Hey everyone, and welcome to this explainer. If you are an 8th grade geometry student looking to absolutely crush your upcoming standardized performance task, you are in the exact right place. Today, we're going to break down how to approach, build, and defend a perfect geometric transformation using digital tools. We're treating this like a true performance task. That means we aren't just looking for the right drawing, we're looking for the precise mathematical reasoning that backs it up.
Here's our roadmap for today. 1. The construction challenge. 2. Precise vocabulary and tools. 3. Modeling the transformation. 4. Verifying preserved measurements. 5. The performance task rubric. And 6. Recap and transfer. Let's get into it.
Section 1. The construction challenge.
All right, here is your student-ready challenge. You are asked to rotate a polygon exactly 90 degrees counterclockwise around a specific center point on a coordinate plane, and you have to do this using geometry software. So this isn't just a quick freehand sketch, right? It requires using the digital environment to perform a mathematically sound rigid motion.
The absolutely crucial point here is meeting these specific requirements to build a defensible solution. You can't just, click and drag until it kind of looks right. You have to purposefully select your tools, meticulously label your starting shape, which is your pre-image, and your final shape, the image. Plus, you literally have to provide a mathematical explanation proving that the measurements of your shape were preserved during the rotation.
Section 2. Precise vocabulary and tools. When it comes to this task, precision is mandatory. For instance, if you're asked to preserve an angle, you need to remember the formal definition. An angle is the union of two rays, or directed line segments, that share a common endpoint, called the vertex. You're going to need this exact kind of language to justify your final work.
To physically build this, you'll be relying on the basic tools within GeoGebra. Specifically, you're going to use the point tool to define your vertices and the center of rotation, the segment or polygon tool to actually build your shape, and the line tool if you need to establish axes or guidelines. Knowing exactly where these are and what they do is foundational to passing this task.
Section 3. Modeling the transformation. So, how do we actually do this? These 4 sequential steps form the core of modeling our perfect defensible solution. First up, you use your polygon tool to plot the initial shape. Second, plot a distinct point to serve as your center of rotation. Third, apply the software's rotation tool, making sure to specify 90 degrees counterclockwise. And fourth, carefully label that resulting figure.
Now, take a look at the critical transition from the pre-image to the image using proper prime notation. When vertex A on your original polygon moves, its new location has to be labeled A prime, with that little apostrophe mark. B becomes B prime, C becomes C prime. This visually communicates to whoever is grading your task that you totally understand the directional flow of the transformation.
Okay, time for a quick spatial reasoning check. Imagine your original point A is sitting up in the top right quadrant, quadrant 1. Where exactly should you expect point A prime to land after we execute a 90-degree counterclockwise rotation around the origin? Think about it for a sec.
Did you guess the top left quadrant or quadrant 2? Because that's the right answer. Why? Well, the rotation smoothly maps the coordinates exactly 1/4 turn counterclockwise around the center point. It's kind of like turning a steering wheel a quarter turn to the left, or watching a clock hand move backward by 15 minutes. Visualizing this before you actually click the rotate tool is an awesome way to self-correct and catch any weird software misclicks.
Section 4. Verifying preserved measurements. According to Standard 8.GA1, we have to verify experimentally that our rigid motion perfectly preserved specific properties. You need to explicitly state in your reasoning that your rotation took line segments to line segments of the exact same length and that angles were taken to angles of the exact same measure. And hey, if your original shape had parallel lines, you've got to state that they remain parallel in the image too.
This whole process brilliantly illustrates mathematical practice 6, attend to precision. This standard reminds us that how we communicate the math is just as important as the drawing itself. You've got to clearly state the meaning of the symbols you use, explicitly label your axes, and verify those lengths and angles accurately to show true mathematical proficiency.
Section 5. Performance Task Rubric.
This 3-part rubric basically covers the core of your grade. First, construction accuracy. Did you actually use the software tools correctly to perform that 90-degree counterclockwise rotation? Second, reasoning. Did you use the HGA1 standard to prove your segment lengths and angles stayed exactly the same? And third,
Communication. Did you use precise geometric vocabulary and flawless prime notation?
Let's do another quick pause check to test your comprehension of this rubric. Imagine you've perfectly rotated the polygon using the software. It's sitting in the exact right spot, but you submit the task without labeling any of the points. Is that enough for full credit?
The answer is a definitive no. You would absolutely lose vital points in the communication category for failing to attend to precision. Look, without mapping point A to A prime, you haven't mathematically communicated the transformation. You've really just drawn two shapes on a screen. The labels literally are the mathematics here.
Section 6, Recap and Transfer. To truly succeed on this task, remember to always map your labels from the pre-image to the image using prime notation. Be sure to use your digital tools strategically, not just randomly clicking around. Always write out your verification that links and angles are preserved under standard 8.g.1, and above all, attend to mathematical precision in everything you write and draw.
Before we wrap up, I want to leave you with a provocative thought to test your true understanding. How would your entire approach, from the software tools you select all the way to how you describe the movement, shift if the performance challenge asked you to model a translation, like a straight slide across the plane, instead of a rotation? Keep that in mind as you practice. Thanks so much for joining this explainer today, and good luck on your performance task. You're going to do great.